Alright, welcome to Chapter 6, Electronic Structure of Atoms. This starts Part 1 of Module 7 for the videos. Alright, so light is mysterious, okay, and it's not really truly understood, but there are a number of different theories and explanations. So light is a form of energy, okay, and it's composed of both electric and magnetic field components. So when we look at light in this chapter, we're going to take a look at both the wave of light and the particle of light, okay, because light behaves as both. I would like to warn you though, this chapter is very in-depth. It's a tough chapter to understand, so you should spend extra time on this chapter reviewing this material. So when we talk about light, we're talking about electromagnetic radiation. And electromagnetic radiation really just carries energy through space. There's many different types of electromagnetic radiation, such as visible light, radio waves, infrared radiation, and X-rays, okay? And they're similar in two major ways. They all move through a vacuum at 3 × 10⁸ meters per second, and they also have wave-like characteristics. Now, if we can take a look at really how light behaves as a wave, and then we'll also talk about, in the next few slides, how light behaves as a particle. So a light wave is similar to sound waves, or any other type of wave, okay? They have both a wavelength and a frequency. The velocity of a wave is really just equal to its frequency times its wavelength, okay? And so when we talk about wavelength, we have abbreviations for it with lambda and frequency with the V. When we talk about wavelength, we're talking about distance between two adjacent peaks or troughs. And we can see that in the figure over here, where you have basically the distance between those two adjacent peaks or troughs, and the frequency is the number of cycles that pass a given point each second. Okay, and so these have units that are either cycles per second, hertz, per second, or inverse seconds. Okay, and when we're talking about the wavelength of light, or we're talking about the energy of light and so forth, we can use this equation, which is just c, which is the speed of light, which is 3 × 10⁸ meters per second, which is equal to the wavelength times the frequency. All right, so light moves very fast, okay, in a vacuum at 3 × 10⁸ meters per second. And light is just energy, and usually energy needs a medium to travel through, okay? If we look at the figure down at the bottom, we can see that when a boat moves through, it makes these waves. That energy is transported through a medium, which is water, okay, transporting that energy. Light does not need a medium, okay? Light is just one type of electromagnetic radiation which carries energy through space, and we can call it radiant energy. So, like I said, the different types of electromagnetic radiation are due to different wavelengths, okay, of these waves. And so this gives these different types of electromagnetic radiations. Each one of these then have differing properties. And so everything that we just talked about is true for other types of electromagnetic radiation, okay? They travel at the speed of light, and they have wave-like properties as well, okay? But when we look at what's termed the electromagnetic spectrum, which is shown in this top figure, basically the visible region is only between 400 and 700 nanometers, or 750 nanometers, okay? And that's the area that we can actually see. One thing to note is that as wavelength increases, moving from left to right, the frequency then will decrease, moving left from right as well. Okay? And so if you have a certain wavelength, you have a certain frequency, you can calculate and figure out which type of, or where you fall in this electromagnetic spectrum. You can also see down at the bottom in table 6.1, which is just basically some basic information about these different parts of the electromagnetic spectrum. Well, when we talk about radiant energy can be composed of either a single wavelength, which makes it monochromatic. An example of that is a laser, okay? Light emitted from a red laser pointer is still going to be 650 nanometers, okay? If you have a green laser pointer, that green laser pointer is emitting light at 532 nanometers, okay? This radiant energy can also be polychromatic, which means it's composed of many different wavelengths, okay? An example of that is a light bulb, okay? So if you shine a light bulb through a little slit, okay, through a prism, you'll get a rainbow, okay? And this is what we term the continuous spectrum, which is shown over on the right, where you get this rainbow, okay? White light will produce a continuous spectrum. But not all light will produce a continuous spectrum, okay? If you were to pass an electric current through a gas, it will emit a light, and that's what's shown down in this bottom left figure. Okay? The identity of the gas and the construction of the lamp will produce color. Thus, different atoms produce radiation at specific wavelengths. Okay? And this produces what we term the line spectra, which is shown on the bottom right figure. Okay? This is a line spectrum. And so we'll talk about why certain atoms give these certain line spectra later in this chapter, but each atom gives a different spectrum. So now that we've talked about the wave nature of light, we can turn and start talking about how light behaves as a particle. So the particle nature of light was really pioneered by two people, Max Planck and Niels Bohr, and they found that they found concepts that could not be explained by the wave nature of light, and they hypothesized that light existed as particles. Okay, and I know there's two people that really pioneered this, but Albert Einstein also had a pretty big part in this as well. So first we can kind of start looking at what we term quantized energy and photons, and we'll talk about this more in the next slide. But there's three concepts that cannot be explained using the wave model of light that we just talked about. The first is blackbody radiation, which is the emission of light from hot objects. The photoelectric effect, which is the emission of electrons from metal surfaces on which light shines, and the emission spectra, which is the emission of light from electronically excited gas atoms. Okay? And the figure on the right is just basically the blackbody radiation. So when we talk about the particle nature of light, we're talking about light carries energy in these little packets. Okay? And so Max Planck believed that light carried energy in discrete quantities, okay, which means it's quantized. Okay? And these chunks are just like little packets of energy. Okay? You can think of them as little sugar packets you get to dump in your coffee or the restaurant. Okay? And we can think of this energy as basically the difference between a set of stairs versus a ramp. In a set of stairs, we jump up to the next level, Whereas a ramp, we just slowly increase up. Okay? And so that's kind of what we're thinking about when we talk about these little packets, is it's like a stair. Okay? You're jumping up. So Max Planck found that the energy that was brought in these packets could actually be calculated with the frequency multiplied by a constant that he was able to define, which is called Planck's constant. Okay? I will give you Planck's constant on an exam, but you should know these equations. E equals Planck's constant times the frequency. Okay? So the energy of a single photon, okay, and a single photon is just that chunk of energy, or that packet of energy, which we can then use to actually calculate the energy of that photon. And so when we break this equation down, E is equal to Planck's constant times the frequency. E is just referring to the energy of a single photon. Right? So if we think about this, then the more frequent the cycles, the more energy that was delivered in each packet. Well, Albert Einstein really furthered this idea by looking at what's called the photoelectric effect. Okay? And he noticed that the higher levels of electromagnetic radiation brought more energy. Okay? And why was that? Well, it was because it had a higher frequency. Right? And so when the energy came in and hit that metal, okay, you can think of it as like, when you play billiards and that cue ball coming in, hitting that metal, and it basically sends all these sends all the other balls flying away. Okay, which is the same way as electrons go everywhere when this comes in and hits this metal. Okay, so electrons are thrown from the atom. All right, so there's some basic information at the bottom of the slide you should know as well. All right, some basics. So now that we kind of talked about how light behaves as a wave and as a particle, now we're going to look at kind of what the Bohr model is. Okay, and Bohr model really helps explain the line spectra of hydrogen. So Niels Bohr believed that atoms have orbits, okay, which the electrons are confined to. And if we look at this top figure on the left, the inside is where we have all our protons and neutrons, right? We have pluses and minus charges, and then we have electrons in these circular orbits surrounding that nucleus. Okay. However, this theory of Bohr, or his model, went against classical physics, but he explained why his model was actually correct. Okay, so when we look at this figure, the electrons are in different orbits based on their energy. So the first inner circle where the E minus is, that's really just our first orbit. Then we have a second orbit. Outside of that, we can have more orbits along that as well. Okay, and so these electrons that may be in the first orbit can jump out to the second or to the third, and then they go back to where they originally were. Okay, and so as they bounce from one orbit to another, they're actually emitting or absorbing energy. So if we would go back to the line spectrum, okay, this line spectrum is really due to electrons jumping from one orbital to another in an atom. So if we go back and think about that same figure we just talked about, electrons are jumping from maybe this first inner circle to the second outer circle or the third and so forth. And we can also see that in this figure down at the bottom left. Okay. We talk about n, okay, the little n, which is a whole number, and it's called the principal quantum number. Okay. Each orbit corresponds to a different value of n. And the radius of the orbit gets larger as it increases. Okay, so you have your n equals 1, n equals 2 is the next out, n equals 3 is the next, and so forth. Okay, so as you get closest to that nucleus, you're at n equals 1. All values of this n have negative energy, but the lowest energy, the most negative, is n equals 1. Okay, and it increases as n, the principal quantum number, increases. So if you just think of this figure down on the bottom left, as basically a ladder. Okay, and the lowest energy state is n equals 1. It's that bottom rung on the ladder. Okay, it's termed the ground state. And as you move up the ladder, each rung is now 1 higher, right? N plus 1. And so the energy increases, and this is termed what's the excited state. Okay, and so as it moves up and then drops back down, you're emitting energy. So the reason we get line spectra is just due to electrons jumping from one orbit to another. Okay. So this figure, I think, actually helps clarify a few different things. And so how do we know this vase is blue? Okay. Well, the modern view of light is just a collection of one or more photons, right, that propagate through space as electromagnetic waves. Okay. Light is energy, and we know it travels in waves. The wave's going to pass through the vase and through the pigment in the vase, which is just cobalt, right? So these waves come in, basically hit that vase, okay? And they hit that pigment, and that pigment in that vase is cobalt, okay? The energy with a wavelength of 475 nanometers is then absorbed by that atom. And the atom becomes excited, and one of the electrons jump to a higher energy level, and then as that electron drops back to its initial energy level, it causes a photon of that same frequency to be emitted, okay? That photon then reaches your eye, okay, and you interpret the color as blue. So that's kind of a simple, basic model of basically how do we see things in different colors. So the last slide of this section is there's different limitations of Bohr's model, okay, but there's also some very important ideas that were introduced by Bohr's model as well. Okay, so try to keep this in mind for a minute. So first, the Bohr model explains just the line spectra of the hydrogen atom. It can't explain the spectra of any other atoms. Okay, electrons do not move about the nucleus in circular orbits. Okay, and we'll see that more as we get into chapter 6. But you can kind of picture it that way. Okay. But the two major important ideas that were introduced is the energy of an electron is quantized. Okay, these electrons exist only in certain discrete energy levels. And energy is involved in the transition of electron from one energy level to another. Okay, so that's jumping on those ladder rungs or moving on those different orbitals back and forth. All right. So that really concludes part 1, but I will make the statement that in this video and in the next video I'm not covering section 6.4, which is the wave behavior of matter. I do expect you to go over, read that, and understand it. But make sure you go back and really read through this chapter. It may take you a couple times to really understand this material. I'll see you in part 2.